Welcome to the next session of Subject Engineering Maths. We were in chapter 3, Differential Calculus, part of calculus. Now in this session, we discuss continuity of a function, L'Hospital rule, etc. So we start the session with L'Hospital rule for limits. The concept is L'Hospital rule. Suppose I want to calculate the limit extends to a f of x by g of x. So that is the limit of ratio of two functions. Generally what we do is, when you are finding limit of a function, as I mentioned in the last session, if the function takes multiple forms or function has modulus, better to evaluate both LHL and RHL. In the rest of the cases it is not required. That means even if you calculate LHL and RHL, you get same. So in that case it is not required. So what we do is, when you are finding the limit of ratio of two functions, replace x by this value a. So in that case, if this limit takes either 0 by 0 or infinity by infinity form, so both are called indeterminate forms. Both are called indeterminate forms. Indeterminate means we cannot measure those values. We cannot determine these values. So when the limit of ratio of two functions takes either 0 by 0 or infinity by infinity form, then this limit must be equal to limit extends to a f dash of x divided by g dash of x. So basically this is nothing but derivative of two functions, f dash of x divided by g of x. This dash represents first order derivative. Note this point. If limit extends to a f of x by g of x, if limit extends to a f of x by g of x, takes either the form 0 by 0 or infinity by infinity, takes either the form 0 by 0 or infinity by infinity, then limit extends to a f of x by g of x equal to limit extends to a f dash of x by g dash of x. Right? Even if it takes again 0 by 0 or infinity by infinity, apply L'Hospital rule once again. So you repeat this process as many times as you can. When you are continuously getting 0 by 0 or infinity by infinity, after some stage you will get some finite value. Okay. Now let us start with some examples. Suppose let us calculate this basic limit. Limit extends to 0 sin x by x. Now let us see, when you replace x by 0, sin 0 is 0, 0 by 0 form. So apply L'Hospital rule. This will be limit extends to 0. What is the derivative of sin x? This is cos x. Derivative of x with respect to x is 1. Now replace x by 0, cos 0 1, 1 by 1. Therefore this limit value equal to 1. It is a very standard limit. So every year they were giving this question. Very basic example. Limit extends to 0, sin x by x is 1, not this. Now let us take second example. This is limit extends to 0, tan x by x. Limit extends to 0, tan x by x. Here also when you replace 0, tan 0, 0, 0. So it is in 0 by 0 form. Apply L'Hospital rule. We get limit extends to 0, derivative of tan x. This is secant square x. Derivative of x is 1. What is secant 0? It is 1. Therefore, limit extends to 0, tan x by x is also equal to 1. Now let us Discuss example 3. Limit x tends to 0, sin 2x divided by, for example, tan 5x. Let us evaluate this limit. One is sine function and there is tan. So when you replace x by 0, it is in 0 by 0 form. So apply L'Hospital rule. The derivative of sine 2x is 2 cos 2x divided by derivative of tan 5x, 5 secant square 5x, 5 secant square 5x. Now replace x by 0, cos 0 1, secant 0 1. So this is a constant expression. So we are getting ratio of these two. So 2 divided by 5. Therefore the conclusion from example 3 is limit x tends to 0, sin ax divided by tan bx. Here a, b are some general real numbers. So the value of this limit is a by b. Now example 4. Limit x tends to a, x power m minus a power m divided by x power n minus a power n. Let us evaluate this limit. Here when you replace x by a, numerator will be 0. And when you replace x by a in the denominator, again 0. So it is in 0 by 0 form. So apply L'Hospital rule. This is limit x tends to a. The derivative of numerator expression is m into x power m minus 1. New derivative of denominator expression n into x power n minus 1. Now replace x by a. Here m is a constant, n is constant. It can be taken before limits. M by n into, this is a power m minus 1 divided by a power n minus 1. Therefore this limit is m by n into a power m minus n. M by n times a power m minus n. Simple calculation. Note this point. Next we evaluate the limit. Limit x tends to 1, log x by x minus 1. Replace x by 1, log 1 0, denominator is 0. So it is in 0 by 0 form. Apply L'Hospital rule. Log x derivative is 1 by x divided by x minus 1 derivative is 1. This is f of x, g of x. So 1 by x is the derivative of this and 1 is derivative of x minus 1. So replace x by 1. The result is 1. This is x tends to 1. Now we discuss properties of limits. The property one is limit x tends to a, k. That is the limit of a constant function. This is nothing but k. So there is no variable part here. It is a constant expression. So the result is k. This is true for any constant k. For any constant k. Second property is limit x tends to a, k1 into f of x. Constant is multiplied with a variable part f of x. You can have either plus or minus k2 into g of x. So therefore limit x tends to a, k1 into f of x plus or minus k2 into g of x. When constants are multiplied with functions of x, they can be taken before limits. Therefore this is nothing but k1 times limit x tends to a f of x. If it is plus, write plus. If it is minus, write minus. So plus or minus k2 into limit x tends to a g of x. For all constants k1 comma k2. For all constants k1 comma k2. and this is called linear property for limits. This is similar to linear property of derivatives and integration. Now property 3. Here between two functions we have either plus or minus. Now replace plus or minus by dot, skip the constants. So limit extends to a f of x dot g of x. Between two functions we have a multiplication symbol dot. Therefore this is nothing but limit extends to a f of x dot, dot is multiplication, limit extends to a g of x. So these are the basic properties of limits. Basic properties of limits. Note these points. Now we discuss two basic limits. The first limit is limit extends to 0, 1 plus x whole power 1 by x. Very basic limit. Limit extends to 0, 1 plus x whole power 1 by x. When you replace x by 0, this base part is 1 and this power part is 1 by 0, infinity. So it is in the form 1 power infinity. This expression is not equal to 1. Generally people may think that anything power 1 is 1. Because infinity is not a finite number. So if it is a finite real number, then you can say that the value is 1. You don't know how many times 1 is multiplied with 1. Even you can argue with me, 1 is multiplied with 1 any number of times, the answer can be 1. That any number you must able to tell me, because you don't know what is the power infinity. Infinity is not a number. It is a symbol to represent a number which is not finite. So here 1 power infinity, this is not 1. This is a wrong statement. So therefore this expression, this limit of this function is a constant e. This is nothing but 2.71. And this is introduced by a famous scientist, mathematician, that is Euler. So therefore this constant is named as Euler's constant. On the name of a famous mathematician Euler, it has been given a named as Euler's constant. Euler is a mathematician who found out this limit. Similarly, the equivalent limit is limit extends to infinity 1 plus 1 by x whole power x. Here when you replace x by infinity, this expression gives 0, 1 power infinity. So here also it is e. But don't think that whenever you get 1 power infinity, it is e. Only in two cases, when you get 1 power infinity, replace the constant e, Euler's constant, 2.71. Suppose if the problem is like this, 1 plus 1 by x whole power 2x. It is limit extends to 0, infinity, 1 plus 1 by x whole power 2x. Now here when you replace x by infinity, it seems to be 1 power infinity form. But this is, you have to convert this limit either in this form or in this form. Therefore this is nothing but limit extends to infinity 1 plus 1 by x into 1 plus 1 by x. Because this is a plus b whole square. So it is a plus b into a plus b. Now this is f of x. For example, I call it as f of x. And this is g of x. So according to properties of limits, limit extends to a f of x dot g of x equal to limit extends to a means infinity here, 1 plus 1 by x into, again same limit repeats. This is property number 3 of limits. So limit extends to infinity 1 plus 1 by x whole power x. Now this is Euler's constant e, this is Euler's constant e. Therefore this is nothing but e square. So only in these two cases, whenever you get 1 power infinity, write it as e. In the rest of the cases, when you are getting 1 power infinity, you to try to convert that limit either in this form or in this form. Okay, so note down these limits. Next concept, continuity, or in simple words we can call it as continuous function. Suppose we have a function f of x and a is a real number, we say that f of x is continuous at a. We say that f of x is continuous at a if limit x tends to a, f of x exists. If limit x tends to a, f of x exists, and limit x tends to a, f of x equal to the functional value, that is f of a. Basically, what is this f of a? Functional value at a. This is nothing but functional value at a. So we have a function f of x. A is some real number. We say that f of x is continuous at this point a if limit x tends to a, f of x exists. So whenever you want to say that a function is continuous at a point a, at first you make sure that the function has limit at this point a. So exists means it's a finite number, and that finite number must be equal to functional value. So whenever limit x tends to a, f of x exists, and that limit must be equal to functional value, then we say that the function f of x is continuous at point a. Note this point. Let f of x be any function. Let f of x be any function and a be any real number. And a be any real number. We say that f of x is continuous at a. We say that f of x is continuous at a if limit x tends to a, f of x exists. If limit x tends to a, f of x exists, and limit x tends to a, f of x equal to f of a. And limit x tends to a, f of x equal to f of a. There you write the point, functional value at a. Functional value at a. Now let us discuss examples of continuous functions. Very, very important examples. Let us start with basic polynomial example. Suppose I have limit x tends to 2, x square plus 3x plus 4. Suppose I want to calculate limit x tends to 2, x square plus 3x plus 4. See, this is my function. So what is f of x? X square plus 3x plus 4. X square plus 3x plus 4. The point is 2. So we need to discuss whether it is continuous at this point or not. Here the function takes a single form. It has no modulus at all. So it is a very basic example. So you can replace x by 2 directly. When you replace x by 2, this gives 2 square plus 3 into 2 plus 4. So this is 4 plus 6 plus 4. This is 14. Basically this 14 is nothing but f of 2. So what is my f of x? X square plus 3x plus 4. Now limit x tends to 2, f of x is a finite number. It is a finite number, and this finite number is equal to functional value f of 2. Therefore, this polynomial expression is continuous at the point 2. Is continuous at the point 2. Therefore, f of x equal to x square plus 3x plus 4 is continuous at the point 2. Is continuous at the point 2. Now let us take example 2. Suppose in example 2, I will take f of x as e power x function. Suppose I want to calculate limit x tends to 3 minus 3 e power x. Now what is f of x in this case? F of x is exponential function. Now it has no modulus, the function is predefined. It takes a single form. So you can replace x by minus 3. This is e power minus 3. E power minus 3 is nothing but 1 by e cube. It is a finite number because e is 2.71. So this is 1 by 2.71 whole cube. It is a finite number. But this value is nothing but f of minus 3. So it is a finite number. So limit value exists at minus 3 and that value equal to functional value. Therefore, e power x is continuous at minus 3. This is continuous at minus 3. Continuous at minus 3. Now let us go to example 3. This is related to constant function. Suppose I have limit extends to 1 by 4. The constant function is minus 2. When you look at the properties of limits, limit of a constant function is itself. So it is minus 2. Now this I can call it as f of 1 by 4. So the limit is a finite value and this limit equal to functional value f of 1 by 4. Therefore this is a constant function. So minus 2 is continuous at 1 by 4. Now let us go to trigonometric functions. That is, for example, sine function. Suppose I have limit extends to 1 sine x. Now the function takes a single form. So directly you can replace x by 1. So it is sine 1. We know that sine of any real number is a finite number. In fact, the maximum value of sine x is plus 1 and minimum is minus 1. So rest of the values oscillate between minus 1 to plus 1. All numbers from minus 1 to plus 1 are finite numbers. Therefore, in fact, sine 1 is a finite number and this value is equal to f of 1. See here, what is my f of x? Sine x. So therefore, in this case, limit extends to 1. Sine x is a finite value, it is a finite number and that finite number equal to f of 1 because f of x is sine x. Therefore, sine x is continuous at 1. Sine x is continuous at the point 1. Now let us discuss last example, that is a trigonometric function which is cos. Suppose limit extends to 4 cos x. Here also you can replace x by 4 directly, cos 4. Now here what is f of x? This is cos x. Cos 4 is a finite number because the maximum value of cos x is plus 1 and its minimum is minus 1 and rest of the values oscillate between minus 1 to plus 1. We know that any number ranging from minus 1 to plus 1 is again a finite number. So therefore, f of x equal to cos x and this value is nothing but f of 4. Therefore, cos x is continuous at 4. Therefore, whatever the examples we have seen till now, all these examples are very basic examples. To show the variation from example to example, I have calculated limits of these functions at different points. In the first case, we have seen the limit of a polynomial expression. This is a polynomial expression. Now in this case, we got the limit at 2. Here limit value at minus 3, limit value at 4, limit value at 1, limit value at 4. In fact, these numbers do not change the continuous properties of a function because you can replace here 3. When you replace x by 3 here, this becomes f of 3. If it is minus 6, this will be f of minus 6. That means it is continuous at all points. Here also the same case. In place of this minus 3, you can write 4. So in that case, you will get e power 4. Again, it becomes continuous. The same case with all the functions. Just to show the variation from example to example, I have calculated limits of all these functions at different points. But their numbers do not change properties of these continuous functions. In fact, all these functions are continuous at all real numbers. And that's why I frequently call these functions as kings of calculus. Because they are continuous at all points. They do not have any drawback in terms of continuity. Okay. So what is first example? It is a polynomial expression. As all we know, what do you mean by a polynomial expression? An expression containing powers of x, positive integral powers of variable followed by some constants is called a polynomial expression. Now here the highest power of x is 2. So it is a second degree polynomial expression. This is a constant function, sine function, cos, exponential function. So my conclusion is all polynomial expressions, constant functions, sine function, cos and exponential, all these are continuous at all points in the entire real number system. So these are very powerful examples. So before writing this conclusion, note down all these examples. Now I write down the conclusion. all polynomials, comma constant functions, all polynomials, comma constant functions, comma sin x, comma cos x, and e power x, are continuous at all points, Now we discuss continuity of a function in a closed interval a comma b. Just now we have seen continuity of a function at a single point. Now we discuss continuity of a function in an interval. So continuity in an interval. Very important concept. Continuity in an interval. Suppose f of x is a function. The interval is closed interval a comma b. Basically, when you discuss closed interval a comma b, it is a set including all numbers from a to b along with a and b. So this is set of all real numbers x such that a less than or equal to x less than or equal to b. This is my set. A is included, b is included, and all real numbers between a and b are included. Now let us discuss the continuity of this function in this interval. We say that f of x is continuous. F of x is continuous in closed interval a comma b if f of x is continuous at all points of closed interval a comma b. F of x is continuous at all points of closed interval a comma b. So this is equivalent to previous definition, but in the previous case we have seen continuity of a function at a single point. Now we were discussing continuity of a function over bigger domain, closed interval a comma b. So analyze its continuity at all points. If a function is continuous at all points in a specific domain, then we say that it is continuous in the total closed interval a comma b. Or the equivalent definition is, if the graph of f of x is continuous, in closed interval a comma b, then also we can say that the function f of x is continuous in closed interval a comma b. So the graphical representation of f of x is important. Graphical representation. Just to draw the graph of f of x between the boundaries x equal to a and x equal to b. So basically x equal to a means it is a straight line parallel to y-axis. X equal to b, it is a straight line parallel to y-axis. Now when the graph of the function f of x between these two boundaries has no breaks, sometimes graphs can be like this. It can be like this. Sometimes it can be a constant function. Sometimes it can be a wave shape function like trigonometric functions sine and cos. Sometimes a polynomial expression like this x squared. So if the graph of a function between the boundaries x equal to a and x equal to b is continuous, then we say that f of x is continuous in closed interval a comma b, right? One simple point is, we have seen continuity of a function in two different domains. In the first domain, it contains a single point a. When do you say that f of x is continuous at a? If limit of the function at that point exists and that limit value equal to functional value. And we have seen varieties of examples, polynomials, constant functions, sine function, e power x, cos x. All these are continuous at all points. Now we extend the same concept over bigger domain closed interval a comma b. So we say that f of x is continuous in closed interval a comma b if f of x is continuous at all points of that closed interval a comma b. But how many points will be there in closed interval a comma b? Infinitely many points will be there. So you need to discuss continuity at all points in that interval. Another equivalent definition is its a graphical representation. So draw the graph of f of x between the boundaries x equal to a and x equal to b. If the graph of f of x between two boundaries has no breaks, it must be continuous. You can have fluctuations. So like this, fluctuations like this. But if the graph has no break between the boundaries x equal to a and x equal to b, then the graph is continuous. Okay. I will tell you one real-time example, just in case of students like you. Suppose a student is attending a college for a semester, in a semester having working days from 1 to, for example, 120. Generally, semester working days will be 4 months. Semester working days will be 4 months. So 4 into 30, 120 days. So let us take closed interval 1 comma 120. Each number represents one particular day. So if you want to say that a student is continuous in the semester 1 comma 120, so how can you say like that? A student must be attending all classes from day 1 to day 120. Yes or no? Is this point clear? So if you want to say that a student is regular to the college, we must go through attendance generally. If he or she attends all working days from 1 to 120, then we say that student has maintained 100% attendance. Or simply in these words, in this terminology, we can say that the student is continuous throughout the college, throughout the semester in the college. Otherwise, if a student has not attended at least one of these working days, then we say that the student is not continuous in that semester. Assume that student is absent on 67th working day. If a student is absent on 67th working day, then he did not maintain 100% attendance. He or she did not maintain 100% attendance. Then that point is called absent day for that. Now in this terminology, in case of continuous function, if a function is not continuous at least one point in closed interval a comma b, then we say that f of x is not continuous in closed interval a comma b. As I mentioned in the earlier sessions, if you want to say that a statement is negative, one simple case is enough. Negative messages will spread very fastly, yes or no? But if you want to say that a positive message, you must convince in all cases. The same case is applicable even in the mathematics world also. So therefore, in this case, the student has absent on 67th working day. Therefore, that fellow is not continuous in the semester 1 to 120. So in this case, if the graph is f of x is continuous, then it is continuous. Note these points. A function f of x is said to be continuous. A function f of x is said to be continuous in closed interval a comma b. A function f of x is said to be continuous in closed interval a comma b if f of x is continuous at all points of closed interval a comma b. A function f of x is said to be continuous in closed interval a comma b if f of x is continuous at all points of closed interval a comma b, or graph of f of x is continuous in closed interval a comma b, or graph of f of x is continuous in closed interval a comma b. Now let us discuss few examples. What we have seen earlier, let us recall same examples along with modulus function, which is very powerful for our contest. Let us discuss examples. First one, suppose f of x equal to x square. Assume that it is defined in closed interval 2 comma 4. So let us discuss continuity of this function in this interval. Now it is a parabolic shape. Let us draw the graph of this. This is x-axis and this is y-axis. So the graph of x square is a parabolic shape. Now this is the boundary x equal to 2 and this is the boundary x equal to 4. So this line is x equal to 2 and this line is x equal to 4. Now between 2 to 4 the graph is continuous, no breaks at all. So the graph is this. So we do not have any break between the boundaries 2 to 4. Therefore its graph is continuous. Therefore the function is continuous in this interval. Therefore f of x equal to x square is continuous in closed interval 2 comma 4. It is continuous in closed interval 2 comma 4. Now let us discuss example 2. So this is f of x equal to modulus of x. So let us discuss its continuity in closed interval minus 2 comma 2. Now actually f of x values are nothing but y values. So here y equal to mod x. But as we know that mod x takes two different forms, it is plus or minus x. Therefore this is a combination of two graphs, y equal to x and y equal to minus x. Now let us draw the graphs of y equal to x and y equal to minus x. Now the graph of y equal to x is a straight line passing through origin. This is x-axis, y-axis. So this is y equal to x, straight line passing through origin. Now let us take y equal to minus x. So this is the line y equal to minus x. Now say for example this is minus 2 and this is plus 2. Therefore when you look at this, the graph is continuous. So this is like this, draw the vertical lines. So dotted lines like this. Therefore between these boundaries the graph is like this, just like V shape. So it has no breaks at all, both are intersecting, both are meeting at origin place. Therefore this is continuous in closed interval minus 2 comma 2. Therefore f of x equal to modulus of x is continuous in closed interval minus 2 comma 2. It is continuous in closed interval minus 2 comma 2. Now when you look at the example 1 and example 2, now I am going for generalization. It is a second degree polynomial expression. Suppose when you take plus 1, the graph will contrast, but still continuity will not be missed. So it is continuous. Similarly, when you replace mod x by like this, suppose if I take a function modulus of x minus 2. Now it is again continuous in the same interval. See, when you take a positive number, generalized value, suppose if I take modulus of x minus k, where k is any real number. In our context, k value is 0. So when k is 0, the function will be mod x. We have seen that it is continuous in closed interval minus 2 comma 2. Now if I generalize this, the function will be turned to modulus of x minus k. So when you replace k by negative value, it becomes x plus something. So therefore the graph will expand, but still it will be more or less in the shape V. If x is a positive value, then x like this, then graph will contrast, but still it will be V shape. So if x values are either negative or positive or 0, shape slightly will change, but continuity will not miss. Therefore modulus of x minus k, it is always continuous. Now this is a second degree polynomial expression. When you generalize this, all polynomials are continuous. Similarly, when you look at graph of sin x, this is a wave shape. Sin x is a wave shape like this. Cos x value like this. So sine function, cos function, even when you look at constant function. So when you look at the graph of a constant function, suppose I will take f of x equal to 2 in closed interval, for example minus 1 comma 4. Now the graph will be like this, x-axis and this is y-axis and this is x equal to 2. I mean y equal to 2, straight line. So this is a straight line parallel to x-axis. So this is minus 1 say and this is 4. So from this point to this point, the graph will be a straight line. So no break at all. So therefore all constant functions are continuous. Sine is a wave shape. There are some fluctuations for the graph of sin x, but still no breaks at all. It is a wave shape, cos function. No breaks at all. Fluctuations can be there. You need not worry whether the graph is smooth or whether the graph is a straight line or graph is rising upwards or graph is down falling like that. You need not worry about these issues. Only thing is you must look at whether the graph has breaks or not. If the graph has no breaks at all, then it is continuous. Therefore, from all the examples, what we conclude is all polynomial expressions. It can be second degree, first degree, third degree, fourth degree, all polynomial expressions, all constant functions as we have seen in 3, and a modulus of x minus k, sine function, cos function, and even exponential function also. So all polynomial expressions, e power x, sine function, cos function, constant expressions, modulus of x minus k. This is very, very powerful. Modulus of x minus k. All these are continuous in all closed intervals. See, again, to show the variation from example to example, I gave you different intervals. But intervals should not change continuous properties of all these expressions. Polynomial expressions, constant expressions, modulus of x minus k, e power x, sine function, cos function. All these are continuous in all closed intervals a comma b, right? So note all these examples. Now we write conclusion from all these examples. Note all polynomials, comma constant functions, all polynomials, comma constant functions, comma sin x, comma cos x, comma e power x, and modulus of x minus k. This is very, very important. And modulus of x minus k are continuous in all closed intervals. All polynomial expressions, constant functions, sin x, cos x, e power x, and modulus of x minus k are continuous in all closed intervals. One more note. If f of x is not continuous, at least one point, if f of x is not continuous at least one point in closed interval a comma b, if f of x is not continuous at least one point in closed interval a comma b, then f of x is not continuous in that interval. Then f of x is not continuous in that interval, and that point is called discontinuity point. And that point is called discontinuity point of f of x in that interval. I repeat once again, if f of x is not continuous at least one point in closed interval a comma b, then f of x is not continuous in that interval, and that point is called discontinuity point of f of x in that interval, right? So this is the end of session.